Welcome to the 2021 Wilmington Spring Workshop.
So I'll be quick here. What I'm going to share today is just like a severe weather refresher. A lot of this is going to come from the rack that we went to a couple years ago, and then a little bit of an adaptation for some of the things that actually work in our areas versus the plains convection that was so centralized whenever we went. And Vic, if you're on, feel free at the end if I miss something to let me know here. Some general tips is what we'll start off with here. And I love already that what we've seen today in our severe weather workshop is, if anything we're going to get out of this, is that the mesoanalyst is key. And I even talk about that here for whenever we did that April 13th outbreak. This was the most important thing to me, along with the observations with, I think it was Dave and Vicky helping us out there. But with the mesoanalyst, you can keep track with tiny changes in the environment that, as a radar operator, make your decisions a lot easier and will eventually improve lead time. So you know that if a storm's going into a more volatile environment, or you know a storm is approaching a sea breeze boundary or some other type of boundary there. So that's very important. And one thing that I do personally that, it's hit or miss based on what your schedule is, but I really like to track storms across other CWAs. So in the days leading up to an organized event, obviously it has to be well forecast. So the April 13th is the one that comes to mind most recently for me. I was watching some of the Alabama WFOs and even into Atlanta, watching their radar and watching how the storms were reacting in the environment. The biggest thing you can get out of this is the sense of mode of the convection as it moves into our area. We typically know this, but you get a sense of what the patterns within the large scale system are going to look like whenever they get to you. Obviously, there's some variation, and if nothing else, this is going to give you some confidence as you go into the following day, if you're the M shift or you're the one being the primary radar guy that day or girl. So now back to the rack stuff. The one thing they taught us specifically was storms that need to get your attention. So there's this process called SRAD, and the first two are screen and rank. And the purpose of this is to find a way to watch potentially intensifying storms. And then once you identify that, you want to follow up with more investigation. And eventually that's how you go through the process of the warning decisions. So I have a procedure called SRAD MRMS. It's in my primary method for doing this, and it's in my RAC 19 severe. And I can put a link to all that with a picture after the fact whenever I put this to the Google Drive. But it basically contains these four elements in a 4-panel: the reflectivity at lowest altitude, the mesh, and the things we're going to talk about specifically here in just a second, the vertically integrated ice and reflectivity at -20. So we'll talk about those more in just a second. RALA is self-explanatory. It's just the reflectivity according to the MRMS, just a nice situational awareness type display. The mesh, always going to overestimate for our area. Last year, I think in June, we had a storm that the mesh had 1.4 over Conway, and we got a report of pea-sized hail. So it's going to be way overestimated for our area. The vertically integrated ice is actually one of the things that I look at probably the most. And the reason I do that is because it gives a good sense of the core of the storm. So vertically integrated ice, obviously looking at the entirety of the storm and trying to get a sense of how much of that storm is containing ice that could develop as it comes down as a core and as it spreads out, causing severe winds or hail in some cases, not so much for our area. But using this is an easy way to get an overview of which storms you need to pay more attention to. And as soon as I start seeing the purples and the whites, I'll immediately flip over to my all tilts panel, or maybe even before that if the environment's a little different. Immediately flip over and start investigating that storm, looking for different signatures. And but this really is what I use to get the attention of which storm I need to pay the most attention to. Obviously, no severe threshold, so it's always going to vary, unfortunately. Which each situation is going to be different, so you have to know that before you go into that. But again, the purple and the whites are what really piqued my interest. And then for pulse convection, especially in the summer, I'll tend to watch this over Charleston and Moorhead's area. I'll watch the MRMS, how they're trending, and then if I catch a peak in the vertically integrated ice before it starts to come back down, I'll then go over to NWS chat and watch for the reports, or the observation person will let me know of any reports going on in Charleston. And that's a good way to kind of get a threshold or an idea of what the MRMS is going to look like before the storm actually develops into something. Since the mode of convection is similar across the CWAs in the summer. And the next, the reflectivity of -20. So this is also in that procedure, kind of the same deal. But again, this is your more standard rule of thumb. So 50 dBz above -20 would suggest a strong storm. Here, it's a little touch and go. That should get your attention, but shouldn't warrant a warning immediately. And then the 60 dBz above -20, that's where you start to get toward that severe storm threshold. And for our area, I would actually suggest that we need a couple of pixels of 60 dBz above -20 to issue a severe thunderstorm. But again, I would suggest that that be done in your all tilts panel. This is just for situational awareness to get an idea that, hey, this storm with 50 dBz at the reflectivity of -20 is going to be one I need to watch. All right. So while these are all great ideas and things to follow, obviously every situation is going to be different. So while you have all these great methods, you want to keep an eye on potentially strengthening storms, and keep an eye on things like the near storm environment. Again, is it entering a volatile environment, approaching a boundary? Storm reports probably should be above that list or on top of that list. Rapidly intensifying storms, we know that all too well. Some things just blow up and it can happen within just a couple of scans. MRMS isn't going to catch that. So always keep an eye on your all tilts, but the SR or the MRMS procedure can really help you identify some of the borderline storms and other things like deviant motions, the obvious signatures, including rear inflow jets for main lines, and then population, of course. So we'll start talking about a little bit of the radar characteristics that I use that, again, were adapted from RAC for some of the things that seem to work best in our area. This is just what works for me. If you have a different process, I'm just trying to widen your perspective here. I'm not trying to tell you what to do, or just trying to give you an idea of things to incorporate into your process. But if something works for you, please, by all means, stick with it. And you want to use multiple radar indicators. You don't just want to see one feature on the radar and say that's what you need to use to warn. And I also rely on the all tilts all the time. I've already said it a few times here, but the upper levels will always support what I'm looking at the 0.5. And if you're seeing it at 0.5, it might already be too late anyway. So here's my screen layout. I wanted to include this, or I was asked to include this as well, just to kind of give an idea of what I look at here. So I know a lot of people like to use the 9 panels. I have a hard time seeing with that much stuff on the screen. So I like the 4 panel. And I collapse the left side. So usually there's these little panels where you can see other products in there. I collapse that so I have more screen space, which is always a difficult challenge for us. But I keep a 4 panel all tilts at all times on my second screen. And I can flip back and forth with the tabs up top to SRAD MRMS. And of course, I've got my satellite up there. But then I never touch the right-hand screen except to issue warnings. That stays warn gen all the time because I want to be able to, if I happen to miss something, I want to make sure I've got warn gen on at all times and it's loaded up and ready to go. And on that same screen, it's a procedure I call beach lightning. And I'll link that as well in my procedure list. But I've got lightning in there as well so that I can see lightning jumps or which storms are producing the most lightning, kind of giving an indication of the how the updraft is strengthening. And then, of course, I've got all my warnings and regional warnings and SPSs. So one of the primary tools that I use, especially for pulse convection, which is the majority of what we have here, organized convection, a little different, and honestly, a little bit easier to see with some of the all tilts, and you kind of get the standard radar characteristics that you would expect there. But storm top divergence for pulse convection has been the best thing I've used so far. It's always best to use base velocity for this, at least in my opinion. Some people can go back and forth on this. I will say though, whenever you're looking at base velocity for your storm top divergence, you want to make sure you find the peak. A lot of people will see one frame of storm top divergence and assign that value, and it might be coming down, or it might not be up yet. So make sure you scroll back and forth to find the peak. But typically for a severe updraft, you want a delta V between the outgoing or the outbound and inbound of about 75 to 100 knots. For stationary storms in our area, which is typically, storm motion around 5 knots during the summer, it's closer to 85 or 100 knots because we really need those cores to get lofted into the air before we can get anything close to severe. If you have delta V above 100 knots, you need to strongly consider a severe. That's a pretty powerful updraft, especially for us. If you have a delta V above 130 knots, make sure you indicate some different text in your warning. If it's above that, you're going to have a significant storm there. Best thing about this, it's not impacted by that beam blockage. So you can scroll up into the upper levels of the radar, not impacted by beam blockage. And then some of the mid-level features like the marks or mid-level convergence, a lot easier to see, and it's above that beam blockage area. Again, if you're at 0.5, it's good to check on every now and then, but if it's in that beam block area, your upper levels are going to be your best sign here. And if you have the storm top divergence with a little bit of the enhanced updraft and the low level convergence, it's going to be a signal that you should really pay attention. Anything above 50 knots for sure. Anything above 50 knots for sure is going to command your attention there. Also put this in here, lightning jumps. This was something they covered in RAC, not extensively, but this is something that I found for our area seems to do pretty well. With the flash density that we have, there are 3 products that I use typically. We have the 1 minute cloud to ground, 1 minute cloud flash, and the 1 minute pulse. As you see maximum and minimums of this in your radar investigation, can really give a sense to what the upper levels and mid levels are doing. Because as you initially expand or separate the ice from the water below, that's a signal that the updraft is maturing, and it's really good for pulse convection. This is another attention getter, I'll say, and not necessarily used in the diagnosis of the storm intensity or structure, but just a heads up there. Shifting gears now from severe to more organized tornado threats. So as we know, vertical continuity of rotation whenever we're issuing tornado warnings is really important, but as we unfortunately know, is not required. And in our area, the latter is fairly common, where we might have a good signature at 0.5 and 0.9. Anything above that is going to be, almost nothing. It's kind of difficult, especially in our beam blocked areas, as we know. But for organized systems, mesocyclones can really signal tornado formation several minutes ahead of time. There was a tech attachment that some of the RAC folks pointed us to, and I've got a little idealized drawing coming up in the next couple of slides that kind of show that. One thing I'll say though, a lot of times you'll need low-level instability, and a lot of times that'll fall on the mesoanalysis. And you want to make sure you're looking at the low-level lapse rates, because if it's unstable near the surface, probably going to be able to get that circulation down. But if it's really stable, it's going to have a hard time. Best view of this, and I think, I think Reed gave a good explanation of this with the Jacksonville and the boundary, kind of a similar situation there. And the best view of these mesocyclones will be above the 1.3 degree scan. They're typically best in the 1.8 to 2. And then convergence beneath the meso in the 0.9 to 0.5 areas will also indicate a strengthening rotating column. And so that can also be a signal for organized tornadic events. Again, if this is a water spout type situation, this isn't going to hold true. Or even if it's like a weak land spout type deal that we get in the summer, or maybe a thunderstorm interacting with a boundary, you might not even see this. So this method is highly sporadic and depends on the storm structure and maturity. That's why the organized events are best for this. So just like a look at how this would typically go. In your first stage, you have the strengthening meso at the 1.9. And you see at the 0.5, you've got a little bit of convergence there as well. And the radar would be off to the northwest here. Yeah. radar will be off to the northwest in this situation. But you have a strengthening meso at the 1.9, and then that meso continues to strengthen and come down a little bit to the 1.3. At that same time, you'll start to see the low-level convergence increase at the bottom or the base of the storm at 0.5 degree. And then the tightening rotation in the mid-levels would start to work its way down. So the rotation at the 0.5 would start to become more from a convergent look and start to rotate around a little bit toward the rotational or cyclonic view. And then as the rotation starts to descend, obviously you get the tightening at 0.9, tightening at 1.3 and 1.9. And then the 0.5 becomes more rotational now. And then the tightening of the rotational column throughout the entire low-level mesocyclone. And there's like I said, the example was in the RAC study that we got, and it was the Southwest Georgia outbreak in February 2000. And I couldn't really find a good explanation of this in a lot of our cases on the west are tropical tornadoes, which show this in some capacity, but it's also so quick that it doesn't even matter. The storm motion is just insanely fast, so it just doesn't really show these types of structures working their way down. Another thing I'll talk about, we're close to the end here. So the beam blockage, with beam blockage, we've got to rely on our 1.8 degrees. Anything above 1.3 is going to be useful to us. The mesocyclones are an easy feature to key on if we have the limited visibility. And again, like I said, the low-level stability is going to play a key role here. And if you think about some of our springtime events, think about the interaction of marine being more stable and land being a little less stable, and how storms propagating from water to land may interact or act as they get closer. And like I said, I always use an all tilts procedure from KLTX. One of the best tools I think we have is having that in conjunction with some of the CC information that we have through the all tilts as well. And I'll say from what I've seen so far, the KCLX Charleston radar, the 0.3 scan that they've implemented is basically useless north of Winyah Bay because it's so far to our southwest. I mean, it's not doing anything for me, at least from what I've seen so far. Our beam height from KLTX is far lower and is able to capture on these, capture some of these rotational features that we're looking for. If you're using KLCX for anything north of that, it's basically like trying to warn on a sail coming into Georgetown County. It makes it all that much more difficult. And I'll mention again, use that SRAD MRMS procedure. I'll link it so everybody can get to it. But using this in conjunction with lightning detection and satellite to see some of the overshooting tops will really help you narrow down which storms you need to focus on in the short term. And obviously, throughout the entire event, you'll jump from one storm to another and work your way down the list, but it's a good process to just keep repeating and keep repeating. But ranking those storms is important. And again, some things are going to be beyond our control here. The weak land spouts, or the Myrtle Beach water spout was a perfect example to me. I went back and looked at that, and there's just nothing you can do. We have shallow rotation. The mesocyclone's not that strong. It's a very difficult situation. So this isn't an answer to everything, was the point I'm getting at here. Another thing that was mentioned earlier, think about utilizing Merle function on the radar in highly blocked areas instead of cells. I didn't think much about cells being a flood asset earlier, but now that I think Vicki talked about that, so that's an interesting use of cells. But for our beam blocked areas, Merle is probably going to be the way to go. Obviously, you have to predict that a storm is going to be solely in that beam blocked area to use it. So not the best, not a great answer to this. I mean, this is a kind of a difficult problem we have, but a tool that we can utilize. And the last thing I wanted to talk about was our warning mentality. Most of our storms will be on the cusp of severe, and it's rarely clear cut. So overanalyzing, by the time you get a signal that says this storm is definitely severe, it's probably going to be too late. So, I don't want to encourage overwarning, but if there's an argument to be made for it, I would put it out. Our users aren't going to distinguish between 50 miles per hour and 60 miles per hour. They're going to be pissed off that half their shingles are gone, or they've got a tree laying in their front yard, or Lord forbid, on their house. I mean, the how hard the wind is blowing in a numerical sense is just for us. That's the only thing that matters. Um, the impacts are what we should be focused on. So my big bullet there: focus on impact rather than how hard the wind is blowing. All right, I think that's all I got. I think I kept it within the time limit, if not just a tiny bit above. But do you guys have any questions?
Yeah, Jordan, excellent. I really appreciate that. And I hope everybody's paying attention to that because in the West, some of those questions that he explained, the answers he gave to some of those questions. So that worked out perfect. One thing you did, you said talk looking at 1.3 elevation
Mm-hmm.
for a mesocyclone. Is that
Yeah.
more consistent with a layer like 4,000 to 8,000? So it could be a different
Yes,
elevation
yes.
angle.
I
Yeah,
should have.
yeah.
Yeah, the degree scans are going to be variant based on where the storm is.
Okay. I
So
just wondered. Yeah.
it does matter what a layer is. I should have
Okay.
specified that, or probably put a layer in altitude up here. But yeah, I was just using an example for the like a storm, ideally at 4,000
Mhm.
at the
Okay.
1.3 scan.
Yeah,
Yeah.
excellent. The other thing on the Merle, that is one of the questions on the West. The one thing about Merle is if we want that second, maybe a second scan at 1.8, which is good, and like it was say, especially in the blocked areas, when you use Merle and you turn it, I think it's 3 to get to 1.8. It's also going to take a second slice of zero point 0.9 and 1.3, so you have to take that into consideration. It's going to be a little longer for your levels above there, but you'll get a second cut of 1.8. I wish we could just say we want a second cut of 1.8 and forget the rest below, but
Yeah.
that's not available now.
Yeah, I'll admit here, I don't have a lot of experience with the Merle function because we're just so, I don't know if it's a comfort thing, but having cell zones a little more comfortable for me than, waiting to get upper level information versus is it already at the surface? I don't know.
Yeah,
That's maybe a social science aspect of
yeah,
this.
yeah, yeah.
No,
Tim, are
same.
you still on? I know Tim uses Merle some, so I wonder what his thoughts were.
Yes, I've used Merle, and particularly in the beam blockage area, I think it could be really, really valuable. Looking at some of the Ocean Ridge tornado data, 2.4, 2.8 degrees, you were getting some really interesting readings up there. But I don't typically look at that. So yeah, I think Merle could pay some dividends, perhaps.
Well, yeah, because
Somebody else
I
had a
mean,
question?
ironically, the beam blockage is where sales is going to fail every time. It's still going to be blocked at point 0.5. So no matter how many extra point 0.5s we have, it's not going to help.
Right. Yep. And I should also mention what Reed was talking about. Probably another good uh, indication is that, just to reiterate, if it's close to the radar, you'll probably need to go up to 3 or 4 degrees before you can see any type of mesocyclone features. If you're in the beam blocked areas and it's moving toward land. Again, all this information is taken from that Ocean Ridge situation because it was so poorly located. But yeah, as it's approaching land, you're going to have to go way up in scans to see any type of mesocyclone features that would be helpful.
Yeah, that's something when everybody takes the west, please when it gets around Ocean Ridge or just when it comes across the coast there, take a look how high up in the elevation scans you have to see some of the rotations and things like that. That really shows it well.
All right, awesome, Jordan. Thank you very much.
Awesome.